So you've found the perfect home. But high mortgage rates have you second-guessing. The Churchill Mortgage team says waiting to buy can be a costly mistake. Try their free 15-minute analysis to see the difference between buying now versus waiting for lower rates. Visit churchillmortgage.com to learn a smarter way to build wealth through home ownership. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027. Waiting for mortgage rates to drop could be a costly mistake. Once rates drop, new home buyers will enter the market and prices will soar even higher. At Churchill Mortgage, you can get a free analysis and learn how to avoid the trap of waiting for interest rates to drop. Buy now and refi later at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. It's us. Thanks for joining us on the Space Nuts podcast. My name's Andrew Dunkley, your host, and with me as always, well, actually he's not there now, Professor Fred Watson.
Yes, he is.
Astronomer-at-Large. I was just introducing you when you walked away. Is all well?
It's Yuri's Day.
It's Yuri's Day today. Yes,
Yeah.
I knew that.
He knew it, but I didn't.
Oh, okay. Three people rang me to tell you.
Okay, good.
60th
Yes,
anniversary.
yeah, that's right. With the 60th, that's absolutely right. Yes.
See how professional we are? We've started perfectly today.
What?
Perfectly. Hello,
I can't
Marnie.
hear him.
Marnie can't hear you because I've got the headphones in.
That's
He's going
okay.
to say hello.
Yeah.
I can't. Hi, Andrew. How are you?
I'm good. How are you? Somebody actually asked the other day if we could get you on the podcast again because they like the Dark Skies project and everything you do. And I said, well, this was Misty West over in the United States. And I said, well, actually, we should get her on again. So there she is. Hello. Say hello to Misty.
Hello, everybody. Happy Dark Sky Week. Last day of Dark Sky Week. So.
Oh, okay. Wow. It's a huge week, isn't it?
Yeah, it is.
And of course, Yuri's Day refers to Yuri Gagarin because today's the anniversary. It is the 12th of April that we're recording this, that he made his epic journey into space. He was up there for, 108 minutes or something?
Yeah,
that was all? Yeah.
And he would have seen a lot less light pollution from space than the astronauts see today. So.
Yes, I can imagine.
On that happy note, I'll leave you.
Okay, thanks. Thanks, Marnie. Thank you. So after that rather unusual start, we introduce Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hi, Andrew. Oh, we are so professional, aren't we? It's just.
Oh yeah, it's a ripper. It's an absolute ripper. But I'm glad Marnie came in and reminded me of that because I did talk about it on my radio show this morning about Yuri Gagarin's epic flight. And yes, 1961.
1961. And that was one of the things that I was still at school then and thinking, what shall I do with my life? I know. There was an eclipse. Yeah, there was an eclipse in the February, and I thought, I think this is going to be my career. But when Yuri went into space, that just clinched it, I have to say.
Yeah. And it kind of was a wake-up call for the United States because I know they were toying with the idea of space travel, but having the Russians get up there at such a tense time between the two countries kind of went, whoa, wait a minute.
Yeah.
We've got to do something about this.
That's right.
And it all began.
Yeah, indeed.
Yeah. Such a sad end to such an incredible achievement when he died too. You would think doing something as dangerous as going into orbit for the first time would probably put you on the brink of some untimely death, but it all went awry on the ground, basically.
Did he? Did he not die in an air crash?
I think it was an air crash. Yeah, I mean,
yeah.
It was a very. I think they've done an inquest that has since suggested that his death was attributed to turbulence from another
really?
aircraft.
Ooh.
Yeah. So that's the way I read it. But he will never be forgotten for what he achieved 60 years ago. So it's Yuri's Day today, the 12th of April. Now, Fred, after that quite straight down the line beginning to the program, episode 248, we're going to just have a quick word about Ingenuity, because that's just about to happen and may well have happened by the time you hear this. We're also going to analyse some particle physics because it's possible we've got the universal model wrong. Possible. Some new findings about the aurora of Jupiter, and some audience questions from Richard in Brisbane and Tom in Toronto, Canada. I know they hate it when I say that, but
So do I.
Do all that. But let's talk about Ingenuity again. We've been talking about it every week for the last few weeks, but that's because it's starting to really get close to this impending launch of a helicopter on Mars, and hopefully by the time this podcast is out there in the ether, it will have happened and been successful.
Yeah, we hope so. The news we have as of today is that a test, I think a couple of days ago, to test fly the rotor was aborted by the helicopter's onboard computer, which said, "Nah, don't like it." It was as they were trying to rev up their. These rotors go around at 2,400 RPM, so they can bite the thin Martian atmosphere. And it was while that was happening that this computer detected some kind of issue, which was not necessarily a problem, but I think there's something called a watchdog timer that shut the thing down because of a potential problem. And so presumably there'll be lots and lots of post-mortems about that to find out what it was. But as far as we know, the first flight is now rescheduled to Wednesday this week, which means that that'll probably be Thursday our time here in Australia. And so, if you're listening to this and it's happened, that's fantastic. And I hope the news is good, and we'll report on it next week, probably.
Yes, indeed. Yeah, it's we've had to record early this week because of impending travels. So we couldn't wait until the actual event before we could record. But hopefully everything went swimmingly. Although if something goes wrong, they can't ditch on Mars because there's nothing to land in, as far as water's concerned. But yes, fingers crossed for Ingenuity's inaugural flight, which has got so many people excited. It's getting a lot of chatter across social media on some of the astronomical and space Facebook pages and Instagram pages and so on, and the news. I mean, you put Ingenuity into your search engine and press the news button, you just get this long lists of stories. So it is quite an astonishing piece of ingenuity if they pull it off, and I'm very confident they will, and very hopeful. Right, let's move on to our next story, Fred, and this is about some experiments that have been done, some dating back some decade and a half, in regard to a subatomic particle called a muon. And this sort of tells the story of the way this particular particle has been behaving, which has got a few people scratching their heads because it's not doing what they thought it should do. And that's led to some speculation that we might have the model of the universe wrong. And they've just released some new data as at this month, the 7th of April, that puts a little bit more weight behind what might be happening and whether or not we have got the universal model wrong. What's your take on this? I know you've been following this story.
Yeah, that's right. So the bottom line is that for some time there are two laboratories involved here. One is the let me get this right, Brookhaven National Laboratory. And 15 years ago, they basically discovered something odd about muons. Excuse me. Now, muons are one of the suite of, it's actually 17 subatomic particles. If you don't count the antimatter particles. It goes up quite a bit if you put them in as well. And of course, they're particles with opposite electrical charge to the normal ones. So the 17 particles, when you include the Higgs boson, muons are one of that suite of fundamental particles. Excuse me, they're a bit like electrons, but different. They are what are called leptons. That puts them in a category which is different from the quarks, which are, I think, a bit bigger if my understanding is right. But the muons are very important, and our understanding of them is fairly complete. They come in to the Earth's atmosphere as cosmic rays. That's sort of where the story started, 60, 70 years ago. In fact, probably more like 80 years ago. So they were behaving in a strange way, and the issue is actually to do with the way they behave in magnetic fields, the way they move, and it's all about spin and things of that sort. I've lost the page that I was looking at about all this. I don't know where it is on my screen, so I'm winging this. But the real issue now is that Fermilab, which is a high-energy laboratory in the United States, have effectively confirmed that original measurement, that there is something wrong with our understanding of the way the muons behave. Why is that important? Just for a start, it's because if you look at what we call the standard model, which has these 17 particles, and the charge and magnetic field are all very, very, very well understood, as is the strength and orientation of the magnetic field, which is something called the magnetic moment. And so, all of those things are well understood. But this muon behavior is confounding that. And this is why people do particle physics experiments, Andrew, because what we're really looking for is holes in the standard model, things that don't fit, because we know from observations principally of the universe, the astronomy stuff, which is why we're talking about this, we know that there are things that we simply don't understand, dark matter and dark energy being the two, perhaps the two biggest. Dark matter is some kind of subatomic particle, we believe, whose identity is completely unknown. There were theories called supersymmetry a few years ago that suggested that these were particles that fit into this supersymmetric framework. Axions and neutralinos were the two things that were being suggested, but there's no evidence that they exist. Until you crack the standard model and find gaps where new physics could creep in, you can't invoke these wild theoretical ideas, because that's all they are. Yeah. So that's why it was exciting. And last week there was a news release from Fermilab that said they've basically confirmed the Brookhaven National Laboratory result, that there is something that we don't understand, and that gets everybody excited. The standard model is, what we're really trying to pull to pieces, in a sense. And
of course, when physicists, particle physicists, get excited, it goes something like, "Gee, look at that, Fred." Yeah, wow, Larry, that's pretty incredible.
Yeah, you probably hit the nail on the head. I think astronomers get more excited, actually, because
maybe.
Sometimes at the telescope they say.
I used the same joke about meteorology the other day, but it's recyclable.
Yeah, astronomers say, "Gosh."
I say that at golf a lot too.
Yeah. So that's the exciting bit, and I have to say, on my reading of this, I thought, yeah, good on them. It's fantastic. And so the plan is to do more experiments. However, on, I think it was yesterday or the day before, 10th of April, over the weekend, essentially a new paper was published. And I'm not reading that paper. I'm actually reading from the conversation article that goes with it. This is by a group of theoretical physicists. So they're the ones who build the mathematical framework within which these things operate, and they have essentially looked at the theory again to see whether that's right. They put Yeah, so the author of that is a gentleman called Zoltan Fodor, who's at Penn State University, and he put it very, very nicely in his conversation article. When the results of an experiment don't match predictions made by the best theory of the day, something is off. 15 years ago, physicists at Brookhaven National Laboratory discovered something perplexing. Muons, a type of subatomic particle, were moving in unexpected ways that didn't match theoretical predictions. Was the theory wrong? Was the experiment off? Or tantalizingly, was this evidence of new physics? And so what they've done, well, I'll read on actually because he puts it in a nutshell. Physicists have been trying to solve this mystery ever since. One group from Fermilab tackled the experimental side and on the 7th of April 2021 released results confirming the original measurements. But my colleagues and I took a different approach. And I'll read on. I am a theoretical physicist and the spokesperson and one of two coordinators of the Budapest-Marseille-Wuppertal collaboration. This is a large-scale collaboration of physicists who have been trying to see if the older theoretical prediction was incorrect. And we used a new method to calculate how muons interact with magnetic fields. That's a long quote from the conversation article, but it absolutely sums it up. What they've done is said, well, wait a minute, the experiment doesn't agree with the theory, and you've checked the experiment by bringing in, this grand new Fermilab results to the table. What about the theory? Is the theory absolutely watertight? And so this group have revamped the theory. They've looked at it again, and what they say is my team's theoretical prediction is different from the original theory and matches both the old experimental evidence and the new Fermilab data. If our calculation is correct, it resolves the discrepancy between theory and experiment. It would suggest that there is not an undiscovered force of nature. So it's a real cold water paper, this, I have to say. But, this is what you've got to do when you're probing really what you might call the final secrets of the universe, things like higher dimensions, all the things that we wonder if we're seeing signs of with the dark matter. When you're doing all that, you've just got to be sure that everything's correct. And certainly this group believe that the previous theory was wrong, and their new theory matches the results that they're getting. So new physics disappears. I'm sure that there will be much debate in the physics world about this. Yeah. It's one of these things that will not be resolved easily. There'll be people taking sides on it and arguing the toss. Meanwhile, more experiments will be done and maybe the results will be hardened up. But if it's the theories that's wrong, that's not going to get you anywhere. So we're in a kind of stalemate position, Andrew. I think it's very interesting. It's a really exciting piece of physics, but it might not mean yet that we can put our hands on our hearts and say we know what dark matter is, because we don't.
So what the theories were suggesting was that muons were acting inappropriately or just doing weird things that they didn't expect. But now a new paper suggests, hang on a minute, they're actually doing what they're supposed to do. That's
exactly right.
Yeah. All right. Well, that throws out my theory that golf balls are made of muons. So it must be some other subatomic particle that we don't know about yet. Well, because my golf balls act inappropriately quite often.
But they do have in common, muons travel at almost the speed of light. I believe yours do as well, is that right?
My golf balls, they barely make 100 miles an hour, which is very sad. Very sad indeed. No, but I think there'll probably be more on this because it's one of those pioneering areas of science and astronomy and physics that they're just trying to figure out. And of course, at the top of the tree at the moment, dark matter and dark energy. And we're sort of only scratching the surface on figuring all this out. You're listening to and watching the Space Nuts podcast, episode 248, with the great Fred Watson and my good self, Andrew Dunkley.
Experiences are what people love the most about travel. Viator is a website and app where you can book travel experiences like hiking Mount Kilimanjaro in Tanzania or enjoying the views while cruising on a catamaran in the Caribbean. They offer everything from simple tours to extreme adventures. With over 300,000 bookable experiences in 190 countries, there's something for everyone. Plus, Viator's travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. When you book a travel experience with Viator, there's always flexibility and support with free cancellation, payment options, and 24/7 service. Download the Viator app now and use code Viator10. That's Viator 10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Space Nuts.
Thanks for joining us on the Space Nuts podcast. Andrew Dunkley here with Fred Watson. And thank you to our patrons. We've had a few more sign up and we really appreciate your support. You can become a patron through patreon.com, through Supercast, or you can make a donation through PayPal. As we've said many times, it's voluntary. You do not have to do it. If you're happy to listen and carry on, that's not a problem at all. No skin off our nose. But if you do want to put a few dollars into the kitty to keep us going, that's entirely up to you, but it would be greatly appreciated. We're ultimately aiming to make it fully listener supported. So the more patrons we can sign up, the closer we are to that target. So jump on our website, spacenutspodcast.com, and click on the subscribe button for more information. Okay, Fred, let's talk about Jupiter. We haven't spoken about Jupiter in a little while, I don't think, but it looks like they've made some interesting discoveries, or a discovery, about its auroral displays. Now, we know what they are. The aurorae are very, very popular and a tourist attraction. In fact, you have many times taken people on tours to see the aurora borealis up in the northern hemisphere. Of course, we've got the aurora australis down our way, which is much harder to see because of the Antarctic region. It's a bit more difficult to get to. But, other planets have these as well, but they've made some new discoveries, have some new insights into what's happening around Jupiter.
Yeah, and this is a story in a way that parallels what we've just been talking about, Andrew, because we've been talking about the magnetic fields of muons, which are subatomic particles. Now we're talking about the magnetic field of the biggest planet in the solar system. So it's the same topic, but going from one side to another. So the thing that has been puzzling about Jupiter's aurorae is that, unlike the Earth, the aurorae occur over a broad area of Jupiter's polar caps. So let me just unpick that a bit, to use a modern term, which I don't like really. Let me explain it a bit. A dog's just walked past the window here. Somebody's dog. We live next door to a vet. You never know what's going to happen.
Probably saw the scalpel and bolted.
Yeah, maybe so. On Earth, the aurorae occur in what's called the auroral circle, which really, or the auroral oval is actually what it's called, which explains it all. So they don't happen at the magnetic pole itself. They happen in a ring around the magnetic pole, centered on the magnetic pole. That's where the aurora are at the strongest. And it's a sort of naive explanation, but this is kind of the case. The reason for that is to do with the magnetic field lines of the Earth's magnetic field. And I mean, I guess we're all familiar with what happens to iron filings. When you've got a bar magnet, you put the bar magnet down and the iron filings trace out the magnetic field. And the field lines normally run from the North Pole round the outside and come back into the South Pole. And they are called closed field lines because they're closed. They end up, both ends of them are on the magnet. Same with the Earth. But there are what are called open field lines as well, which are field lines that just head off into space. And you can sort of imagine that will be the case. And so the open field lines are the ones inside the auroral circle. And so that's why you don't see aurorae there, because the subatomic particles from the sun are not spiraling down like they do in the auroral oval region and lighting up the atmosphere by exciting the atoms of the atmosphere. So that's why it's an auroral oval, because of where the field lines actually go into the Earth. Now Jupiter is different, because apparently on Jupiter you get aurorae within the whole of the polar cap. It's not just within that auroral circle, and this is until now has been the puzzle. And there is some new research which seems to shed light on it. And it comes from, a number of institutions, including the University of Alaska Fairbanks Geophysical Institute and the University of Hong Kong, a number of collaborations, 13 researchers, I think, have made this key discovery about the aurora. And once again, it depends on theoretical models. We've talked a lot about theoretical models today, Andrew. But the theory is that aurorae only occupy this zone where the magnetic field lines actually close up and disappear into the Earth, and not elsewhere. But the new theory that these scientists have propounded is essentially one that says the aurorae can actually occur elsewhere. They can occur in open field lines. So let me once again read from. Actually, this is a piece not written by these. Actually, it is. Yeah, so I can read it legitimately. It comes from the University of Alaska Fairbanks. It is their press release, and it says. Jupiter has a polar cap in which the aurora dazzles, but has puzzled scientists. The problem is that researchers were so Earth-centric in their thinking about Jupiter because what they have learned about the Earth's own magnetic field. So what they've done is used computer modelling to help. Their research revealed a largely closed polar region. That means where the field lines are going back into Jupiter, with a small crescent-shaped area of open flux. That means where the field lines are going out into space, accounting for only about 9% of the polar region. And the rest was active with aurora, signifying closed magnetic field lines. But Jupiter, it turns out, possesses a mix of open and closed field lines in the polar caps. And Dr. Delamere made this comment: there was no model or no understanding to explain how you could have a crescent of open flux like this simulation is producing. He said, it just never even entered my mind. I don't think anybody in the community could have imagined this solution, yet the simulation has produced it. To me, this is a major paradigm shift for the way that we understand magnetospheres. That's the magnetic region around planets. It raises many questions about how the solar wind interacts with Jupiter's magnetosphere and influences the dynamics. So basically, you've got a situation quite different from the Earth. And what they're putting that down to is possibly the rapidity of Jupiter's rotation, because Jupiter goes around once every 10 hours, Andrew, compared with our once in 24 hours. Plus the fact that you've got this enormous magnetic field around Jupiter, so in a very, very large magnetosphere. And so what they're suggesting is that they reduce the impact of the solar wind, and it means that perhaps the magnetic field lines are more likely to be closed up on Jupiter. It's that there's another thing about Jupiter though that's weird, and we know that this comes about because of spacecraft measurements. But Jupiter's moon Io, which is the innermost moon, highly volcanically active, it's kind of electrically linked to Jupiter because you can see transfer of material along the magnetic field lines from Io to Jupiter itself, in fact to the polar cap. So there's all kinds of complexities there, but at least there is something that is better understood because of this theoretical model of Jupiter's magnetosphere.
you talk about the magnetic field of Jupiter, and obviously, trying to think of Jupiter the way we think of Earth was probably always going to run us into a brick wall, because they're very, very different planets. Is Jupiter's magnetic field generated in a different way to that of Earth?
We think it's probably the same, but you're absolutely right to focus on that, because we don't know what's at the middle of Jupiter. I mean, the Earth's magnetic field is generated by the iron core, and that seems to be likely that something like that will be at the middle of Jupiter. But it might not be iron. Some people postulate that Jupiter has a core of metallic hydrogen. Work that one out. Hydrogen that's turned into a metal, which would be conducting. So, that might also generate the magnetic field. But honestly, we don't know. Juno, the Juno spacecraft, which is still active around Jupiter, one of its tasks is actually probing the innermost secrets of Jupiter in terms of its core, if it has one, if it has a solid core. We don't even know that it has a solid core, but it seems likely, given this magnetic field that's got to come from somewhere. So we might know more when Juno's mission is finished. I mean, there are probably papers that are coming out on this now that I haven't really been keeping up with, but it's probably our best assistance to understanding what's going on with Jupiter is the Juno spacecraft.
Yes, indeed. All right. Well, it's taken a while, but we've suddenly decided we need to treat Jupiter like something that it's not akin to Earth, which makes sense. I mean, we're a rocky planet. It's a gas giant. I
know. It's what is
not
it?
11 closely related second cousins twice removed.
Yes, that's right. But what it has in common is it was made from the same cloud of gas and dust. So you kind of know what it's made of, but you don't know how that's distributed within Jupiter.
Yeah, we don't know what lies beneath, but some fascinating findings. This is Space Nuts, the podcast about space science, astronomy, and all sorts of other stuff. Thanks for joining us on episode 248.
3, 2, 1.
Space Nuts.
This is Space Nuts, episode 248 with Andrew Dunkley and Fred Watson. Fred, the other day somebody pointed out that for 2 weeks in a row we both wore pink shirts.
Yeah, we did. I noticed that too.
Did we do it on purpose? No, it was a complete accident. But I noticed today we're both wearing navy blue.
Yep, we are. Yep.
So, and of course, if you follow us on YouTube, you would be aware of that because you can watch us. I don't know why you'd want to see our faces. My wife doesn't want to see my face most days, but look, thank you to our YouTube followers, all 1.65 thousand of you. And, if you know anybody else who wants to follow us on YouTube, let them know because the numbers are ever growing. And we are just about, Fred, this is really exciting news. We're just about to crack 1 million downloads of the podcast.
Oh,
I knew that would come as a surprise to you, but at last count, we'd had 984,000 downloads. So probably by the end of the month or into May, we'll probably crack the 1 million. So thank you to everyone who's been supporting the podcast and for listening for as long as you have. And many have been listening for a long time, some from the very beginning, some from about episode 70, and some started today. And if you are one of those, welcome. Hope you stick around and enjoy the podcast. Whatever platform you listen on, whether it's Apple Podcasts, Google Podcasts, Stitcher, there's a long list of them. Whatever your favourite platform is, you'll probably find us. And it's time to do some questions, Fred. So let's get straight into it. And we start with Richard in Brisbane. Hi, Fred and Andrew. Richard here from Brisbane. That's a coincidence because that's where I thought he was from. Love the show, love the content, love the dad jokes that Andrew seems to have an endless supply of. It's very sad and true. My questions are in regard to dwarf galaxies. Question 1, is there a common type of galactic centre for dwarf galaxies? I imagine they have some sort of central massive object, But is it a supermassive black hole or a solar mass black hole, a quasar, something else entirely, or nothing at all? And question 2, when a dwarf galaxy merges with another galaxy such as the Milky Way, what happens to the central massive object? I assume it's eventually absorbed by the supermassive black hole of the larger galaxy. And if that's so, does it separate from the dwarf galaxy's remnant stars, or do they get sucked in together? Question 2.5. Add to this, what happens when two dwarf galaxies merge? Thanks for doing the job you do, guys. Please keep it up. Well, we were about to stop, but yeah, okay, we'll keep going just because of you, Richard. Let's start with, is there a common type of galactic centre for dwarf galaxies?
Yeah, it's a really interesting question, and there probably is. And so I, did a bit of research on this question because I didn't really know the answer. And there is some work that was published last year, actually rather more than a year ago, which it actually comes from Montana State University and other institutions. And the interesting aspect of this is it answers several of the questions in or the parts of Richard's question, because what this group found was massive black holes in 13 dwarf galaxies. Excuse me. Sorry. Beg your pardon. They are now among the smallest galaxies known to host such massive black holes. So it's this is a new insight into our understanding of dwarf galaxies, because I think the consensus was, until relatively recently, that a dwarf galaxy would not have a supermassive black hole at its centre. And so that's, you when you look at pictures of dwarf galaxies, they're pretty ragbag looking things, they're not terribly well formed. They often don't have spiral arms, although some do. The two Magellanic Clouds that orbit our own galaxy, in particular the Large Magellanic Cloud, which you and I see in our skies, you particularly because you live in a fairly dark region of the state where you can see the Milky Way and the Magellanic Clouds. The Large Magellanic Cloud just has stubs of spiral arms. It's got a little bit of spiral structure and a kind of bar across the middle joining them up. And that's a characteristic of a much larger galaxy, but it's only a dwarf. And it's probably smaller than it started out as well, because it's having certainly its gas is being removed by the gravity of the Milky Way. Something called the Magellanic Stream is streaming gas off the two Magellanic Clouds. You see it in radio telescopes. So this result that came out last year is really interesting, because it does highlight that these dwarf galaxies do have black holes at their centre, and some of them are what we call intermediate mass black holes. The ones that seem to have gone walkabout, where we've got the stellar mass black holes, the supermassive black holes. These are intermediate. So to come down to just a few of the results, they spotted 13 massive black holes in dwarf galaxies located within 1 billion light years of our own galaxy. So they're relatively nearby, which they'd have to be because they're fainter than the giant galaxies that we're normally looking at. All of the 13 galaxies are only 100th of the mass of our own Milky Way galaxy or smaller. So they're 100 times smaller than the Milky Way.
Right.
But they've got black holes. That makes them among the smallest galaxies known to host massive black holes. And in fact, this work was announced last year, the beginning of 2020. The American Astronomical Society they have an annual meeting every January, right at the beginning of January. It was in Honolulu last year. Sadly, I couldn't make it, mainly because I was in far northern Scandinavia watching the aurora, but never mind. Anyway, that's where this result was published. But here's the crunch, Andrew. The black holes average about 400,000 times the mass of the sun. So that is right in the middle of the intermediate black hole range. It's a bit on the big side. You're getting towards, not far off 1 million there. But it's yeah. So they really are intermediate mass black holes. But there's another punchline to this, which I think is quite extraordinary. These black holes were actively, eating material around them. But in half of the galaxies, the black holes weren't at the middle. They were kind of wandering around in the galaxy. So that's rather unexpected. You would expect that the massive black hole or a supermassive black hole at the middle of a galaxy is going to be plonked right in the middle because it's where, the gravitational center of that object is. But in these dwarf galaxies, that's not the case. And I suppose that suggests that, there may be, the dwarf galaxies might be easily disturbed by bigger galaxies, so their structure might have been kind of pulled out of kilter.
Yeah, that makes sense.
Yeah, there's a couple of quotes from the authors of this work. One is, "This work has taught us that we must broaden our searches for massive black holes in dwarf galaxies, but beyond their centres, to get a more complete understanding of the population and learn what mechanisms helped form the first massive black holes in the early universe." And there is another quote, "We hope that by studying them and their galaxies will give us insights into how similar black holes in the early universe formed and then grew through galactic mergers over billions of years, producing the supermassive black holes we see in larger galaxies today, with masses of many millions or billions of times that of the Sun."
So that probably answers, to a certain degree, the question about what happens when dwarf galaxies merge. The black holes would merge too.
Very probably, that's right. They've only found one black hole in each of these galaxies. If they'd found two, maybe that would be some evidence for an incomplete merger, if I could put it that way. Because I think normally, when galaxies merge, the black holes merge too. There's one interesting aspect of this, though, that there is still a school of thought. It's quite an old way of thinking and is not agreed upon by everybody, but the globular clusters in our own galaxy, globular clusters are really dense star clusters. The two brightest and biggest are in the southern hemisphere, again, which is one reason for putting telescopes down here. Omega Centauri and 47 Tucani are the two biggest of these objects in our galaxy. And some astronomers think that what you're seeing in a globular cluster is the stripped down core of a dwarf galaxy that's had all its outer stars pulled off by the gravitation of the Milky Way, but that the core of that galaxy is so gravitationally compact that it resists the what we call the tidal effects of the Milky Way and stays intact. And that actually makes a lot of sense, particularly because there have been one or two what you might call, I suppose you still call them intermediate black hole candidates discovered inside globular clusters. We think there are some globular clusters that have black holes in them, which highlights the possibility that maybe these are the the final remains of some galaxies that got too close to the Milky Way.
So basically, everything Richard's asked is possible. To a certain degree.
It sounds like all the answers are yes, including question 2.5, which is what happens when two dwarf galaxies merge. Their black holes probably merge too.
Okay, what about the quasar theory that he came up with?
So quasars are a slightly different category, and they're kind of extinct now because they're a product of the early universe where you had the supermassive black holes within galaxies really actively consuming the material around them. And they're so active that they're very powerful emitters of radio waves and visible light, in fact. And so the quasar regime has gone, but maybe, scientists wonder if all galaxies go through a quasar phase early in their lives.
Yeah,
that may not extend to dwarf galaxies because you need a pretty big supermassive black hole to really kick off this process and get the kind of activity that you get with a quasar.
There you go, Richard. So the answers to your questions are yes, perhaps, probably not, and maybe.
But not necessarily in that order.
No, not really. But thanks for your question, Richard, and hope things are going well in sunny Brisbane. I'm actually going up to Queensland later this year. We've got to go to a wedding. So hopefully all will be well come August, and I'll remember to take my hay fever medication. Last time we went up there for a wedding, we went in August, and I thought, that's only August, she'll be right, still winter.
Yeah. Oh, no, not in Brisbane.
Got me good, because I was too far north. But thanks again, Richard. Now let's move on to a question or two from Tom in Toronto, Canada. Hello, Fred and Andrew. I'm a subscriber and admirer of your podcast since about episode 70, coincidentally. I have two questions for Professor Watson. I love this. Your Wikipedia page mentions few musical compositions you are a part of. How does the cosmos inspire your music, and does music inspire any thoughts or ideas you might have in your astronomical research? And then a really serious question. Could black holes be safely used in gravity assist? Greetings from snowy Toronto. Well, it was snowy New South Wales, Victoria and Tasmania this week. So as we in the north and southern hemispheres go through our seasonal changes, we're all sort of experiencing the same thing at the moment. But yes, your music, Fred. He's interested in your music.
Well, where to start? So I think it's fair to say, Andrew, I grew up in a musical family, and
so
my dad was a swing, but he played in a swing band, and indeed my brother still does. They were both drummers, or they are. My brother still is a drummer. Although I have to say,
we won't hold that against them.
He doesn't. No, I know. He gets all the drum jokes. Yeah, he doesn't get many gigs these days for obvious reasons. So there was always music, but it wasn't just swing music. I mean, this is back in the 40s when I was a little one. Classical music was there as well, and that's what really got me hooked. I like pop music, but classical music has been something that has been a major part of my life throughout my whole life. And to be honest, Andrew, I'm really glad about that, because it often provides you with a way of getting away from the world. It's a really sort of solid thing to be able to listen to a piece of music that you know is going to be your happy place. Whether it's Beethoven or Sibelius or Brahms or whoever it is, it's all great stuff. So Steppenwolf, yeah, I can do that as well. Because I've got a fairly broad musical taste, and so that in the 60s, I was heavily into the Beatles and the Stones and all the stuff that was going on then. But that's the other side of it. So my classical music is not entirely confined to listening, and I'll explain that in a second, but mostly because I don't play an orchestral instrument, for example. So I've never sat in an orchestra and played a violin or something. However, I did learn both piano and guitar. And in the folk era, in the 60s and 70s, I did a lot. I played in folk clubs all over England and Scotland, hung out with the likes of Jerry Rafferty and Billy Connolly and people like that who were up and coming musicians at the time. I still play occasionally, but not in any sense the way I was meaning to. I thought I was going to become a professional musician. I'm quite glad I didn't, because I wasn't actually, when I look back on it, I wasn't all that good. Never mind. The guy I played with was, though, he's still a professional in Scotland, Kenny Brill. We were two halves of a band called the Bradford and East Fife Ready Mix Concrete Company. Worked that one out. Anyway, the science comes into that because for the last 50 years I've written daft science songs, which I perform at Signs in the Pub and things of that sort. Yeah. But the classical, in some ways, is more related to the astronomy, because I got very friendly with, because through his work, listening to his work on the radio, with an Australian composer by the name of Ross Edwards. Ross is one of Australia's foremost classical music composers. He actually composed the piece that was played on the sales of the Sydney Opera House on the 1st of January 2000 with an audience of 2.5 billion people. It's called Dawn Mantras. It's a beautiful piece of modern classical music. And not long after that, we hooked up the idea of making a musical journey through the night sky. which is his Fourth Symphony, and it's a choral work. It has 2 choirs to sing it, and I wrote the words, which are essentially the constellations that we recognise and stars that we recognise in the Western world, juxtaposed with the constellations that Aboriginal people recognise here in Australia. Now, they vary from place to place, so I just had to take selections. But it actually won an award, Andrew. The 2008 APRA Award for the Best Choral Work of the Year, because it came out on a CD. So
APRA being the Australian Performing Rights Association.
That's exactly right. The 2 things are very much intertwined in my brain. And really, I can't answer Tom's question because I don't know how it is that these things inspire each other, but they definitely do. I do, when I'm writing, I often like this kid's book. I know it sounds daft to say it in a kid's book, but I'm often subconsciously aware of the structure in a piece of music. The exposition, the development, the recapitulation in a piece of what's called sonata form often goes into the way I write things. You set off with an idea and you bundle it around a bit, and then you come out with the same idea but in a different form at the end. Once again, I don't think that answers the question. Let's get on to the real question anyway.
Fascinating, though. Fascinating. Yes, he says, could black holes be safely used in gravity assist? I assume this is like space travel.
Yeah, it's an interesting thought, and what little I know about the mechanisms of gravity assist suggests that I don't think they could, because...
Too big?
It's more that they don't have... that they don't have structure. So, look, I'm kind of guessing here, so these are ideas pulled out of the air. But gravity assist is weird because if you think about it, what's happening is you're flying a spacecraft close to a planet, it's feeling that planet's gravity to increase the speed of the spacecraft. But when the spacecraft's gone past, its gravity is trying to slow it down. And I think if you had a single point, that would be what would happen. You wouldn't gain any momentum from the encounter. The speed you gained on the approach to the black hole, assuming you're going fast enough not to get sucked in, would match the speed you'd lose on the way out. So the net effect would be 0. Because, as I understand it, it's to do with the planet's rotation and the direction that you approach it in relation to its equator that actually gives you the gravity assist. So it's to do with the structure of the planet itself that you can make this momentum change to give momentum to the planet. Sorry, to take momentum from the planet to assist your spacecraft in its journey. So I think the answer is probably no. Even, I'm not sure anybody would want to fly a spacecraft close to a black hole anyway, in case...
I'm sure there are people who would want to, whether or not you'd be capable of it, and come back to tell the story. That'd be a different thing, I imagine. But, okay, so probably not is the answer to that particular question.
I will try and follow it up, though, because it's a really interesting question. And it feeds into why gravity assist works at all.
Fascinating. All right. Thanks, Tom. Thanks, Richard, for your questions. We knocked over a couple of more of those text questions that have been racking up for the last, 10 years. But we'll knock off some more. But if you do have a question for us, don't forget to visit our website and click on the AMA link. And you can send us a text question through the email interface, or you can use your recording device, whether it's through a tablet or a smartphone or a computer, and just tell us who you are, where you're from, and ask your question. Happy to run audio questions as well, which we've been doing a lot of lately, but catching up on the text questions too. And that's pretty well it. And thank you again, Fred, as always. It's great to see you, and happy trails, and we'll catch you again next week.
Sounds great, Andrew. Same to you. All the best. Speak soon.
Professor Fred Watson, Astronomer-at-Large, part of the team here on the Space Nuts podcast. Hello to Hugh in the studio, who works feverishly to put it all together and adds the nuts and bolts and finds the silly pictures that he puts on the graphics when we put them online. And from me, Andrew Dunkley, thanks again for joining us. We'll see you on the very next episode of the Space Nuts podcast. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.